So let me start by asking if you have any questions over any of the problems I've given you. Problems practice for the test. Not really problems to turn in. Any questions on those? As in those Word documents that have the problems in them. You guys are okay with all that? Okay, good. So I'll go over a couple of more topics, and then I'll leave room for questions. And if there really aren't any questions, we'll probably cut it a little short today. I don't want to add anything beyond a couple of little things. Did we decide white doesn't work? Can you see this? Oh yeah, you can see that. That's good. I broke the yellow chalk. We'll start where we left off last time. So I gave you some questions at the end of this chapter. But this is one of the examples in the chapter. So let me just go through this. Did we do this one? I guess we did. So that's a combustion reaction. So remember that if you're looking at this reaction, what you're really looking at is a molar relationship between these two things, and then these two things, and these two things, these two, and these two. There's 6 relationships in that equation that you see there. You remember that? For instance, and of course, this is another one of those cases where in chemistry we don't write the 1. If there's nothing there, then it means 1. But let me write down C6H12. 8. No, that's a 6. Okay. So the first relationship I would write down is so you remember that? This is where we left off last time. All right, so you have 6 relationships like that here. Convert grams to moles. Well, okay. Okay, they give you the systematic thing. All right, determine how many grams of water, so that's the water, is produced, and this is oxidation of 1 gram of glucose, and if that's glucose. So what's the first thing we have to do? Well, I'll give you this much. We're relating water, this H2O, to glucose, which is this. So I'll go ahead and write that down. 1 mole of C6H12O6 to 6 moles of H2O. Molar mass is the next thing we need. We could calculate the molar mass for this, and this, but this is saying how many grams of water. So it says grams, so we're going to have grams per mole for water. And then it gives us grams for glucose, so we need grams per mole for glucose. So that's this. For glucose, it would be, there's our carbon, there's 6 of them. For hydrogen, there's 12 hydrogens, and 6 oxygens. And you guys have your periodic tables? If you've got your periodic table out, tell me what it says for carbon. 12.01, and for hydrogen, 1.01, oxygen is 16, and I'm not doing that in my head. 6 times 12.01, $72.06. 12 by 1.01 is going to be that. 6 times 16 is 96. And all that together, $12.12. Did I end on this problem last time? I must have done one with glucose in it. That seems too familiar. I did do this one, didn't I? I'll do a different one if I've already did this one. I'll finish it. Okay, grams per mole. And then water. You got 2 hydrogens and 1 oxygen. So hydrogen 1.01, oxygen 16.00. Sum those up. So we're going to need this, and we're going to need these 2 things, and then we can solve this very directly. We're given 1 gram for glucose, so 1 gram, I'll say C6H12O6. Now, we're going to use grams per mole for glucose, which is this. This is so I've just rewritten this way, and I'm going to use C6H12O6 for the label on the unit. So that, but I want grams on the bottom, so I'm going to go 180.01 grams C6H6 H12O6 to 1 mole. So that's how we start. Now I've got moles of C6H12O6. So I'm going to use this next, but I want this on the bottom, so the moles will cancel. So 1 mole C6H12O6. H2O. Next, I'm going to use the grams per mole for water. H2O to 1 mole of H2O. It's this that I'm going to use next. I want moles on bottom, so I use it exactly the way it is. Grams of H2O, 1 mole of H2O. That's how you'd solve this. You guys good with this? It's all, everything cancels. This label goes with these grams. So you have grams of H2O here, but that's not going to cancel these grams because that's grams of H2O and that's grams of glucose. So those cancel each other. These cancel each other. These cancel each other. This is actually, I wrote that wrong, actually. I should have done that, 1.00. This, 1.00. So we do get significant figures there from that. This is exact, this one is exact, this one is exact, this one is exact, and these integers, that's 6, yeah, this 6 and this 1 are also exact. So all we're dealing with for significant figures are these 4, these 5, and these 3. And the least number of significant figures here is 3, so the answer needs to be in 3. I guess I'll go ahead and calculate it, but the important thing is to know how to set it up. 6 times 18.02 divided by 180.01. So my calculator says that's what my calculator gives me. If it's going to be 3 significant figures, then it's going to be these digits. The 6 rounds the 0 up. And the units are going to be grams of H2O. So that's not in standard scientific notation. Standard scientific notation would give you, move the decimal one place, and I won't need that. So that's how you would solve that. You guys okay with this? All right. So since we did problems like that last time, I wanted to warm up with that one. The next thing we have to do, those of you who took a chemistry class before, do you remember limiting reactant? At least the phrase or the idea. Are you good with it? Cool, I get to explain it to you. So limiting reactant is just like these types of calculations, but you have to figure out which one's the limiting reactant first. Guess it's this one I want to do. Let's do this one. Okay, and notice this is asking how many moles. So we're not going to need grams per mole here, but there could be grams per mole for this. But if it's just moles to moles, you don't need the grams per mole. You won't need this, you won't need this, and this will be in moles. So you're just using something like that, but here, let me show you. So let me explain something about these reactions. If you see that, what you've been asked before in the previous section, you see in this section, what we were doing before is it would just give you one of the reactants. So that's a reactant, and over here are products, although there's just one product in this particular reaction. But it's giving you X number of moles of this reactant and X number of moles of this reactant. Here's the thing, let me write a different reaction down that's a one-to-one relationship. If you did NaCl plus, what should I do? Silver nitrate. And you got as products this is actually balanced as it is. I don't need to put any coefficients here. So it is, all the relationships here are 1 mole of NaCl to 1 mole of AgNO3, 1 mole of NaCl to 1 mole of NaNO3. So all of these are ones, here, 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 and here. So you look at a reaction like this, and the truth is, if I put, how do I put this? If I had 1,000 of these, say in a beaker of water waiting to react, and I put 2,000 of these in that same beaker, you're only going to get 1,000 of these to react until that's all gone, and there'll be 1,000 of these left. You follow that? You do? Can't really see y'all when this is doing. Let me say it again. If there's 1,000 of these drop down into a beaker of water ready to react, I put these in there to make it react with that, but I put twice as many of these as I put these in. You're only going to get the first 1,000 of these to react. Then you're going to run out of this, and that second 1,000 of these will just be sitting there in the water. Does that make sense? Then I can say 1,000 and 2,000 because this is technically a one-to-one relationship. So you could walk up to a beaker of water and think it out ahead of time and put exactly the amount of this and exactly the amount of this, so the react such there will be none of the reactants left and only products. You can do that for sure, but it's actually very typical to measure very carefully one of the reactants and then put the other reactant in there and a bit of excess to the other one. So you really only have to measure one very, very analytically. But here's the point. The one that there's less of, that's going to be used up compared to the other one that there's too much of, you have to use, and this is the key to this limiting and excess thing, you have to use the one that was limiting to predict the products. And to figure out which one is limiting and which one is excess, it's just something you have to do ahead of time. And then after that, it's just like the calculations I did last time. It's just like the calculation I just finished here. Meaning, there are 6 relationships here. 1 mole of NaCl to 1 mole AgNO3. So that's these two related to each other. And then there's this one related to this one. Let me write these out. NaCl. So that one, there's that relationship, and these are all 1 mole. I just used them all. I just used one that had them all the same. So there's that relationship. There's also NaCl to AgCl, and it's 1 mole. So that's that one and that one related to each other. And then, and there's also this one related to this, and this one related to this. But if this one's limiting, then if I'm going to predict the products, if I'm going to predict how much NaNO3 is produced, or if I'm going to predict how much AgCl is produced, I have to use the one over here that's limiting, meaning I have to use, let me write this other one, AgNO3 to NaNO3. AgNO3. Yeah, these are all 1 mole. 1 mole. And then AgNO3 to AgCl. Yeah, these are all 1 mole. I go through the trouble of figuring out which one is limiting and which one is excess, and I decide this one is limiting. That means these, the AgNO3, that's not going to predict how much of this we get, and it's not going to predict how much of this we get. we can't use these. Because we'll have that 2,000 of these in there, but really only 1,000 of them reacted. But the 1,000 of this that we put in, that's going to predict how much product we get. That's the whole point of figuring out which one's limiting and which one's excess. You need to know which one is limiting, and then any predictions on how much product you get is going to come from this one was limiting. Those we have to use. The NaNaCl was the limiting one. This one was in excess, the way I described it. So we have to use this to predict any NaNO3 we get, or we have to use this to predict any AgCl we get. We can't use the AgNO3 because it was in excess. You follow that? So the whole limiting excess thing is you go through the trouble to figure out which one's limiting and which one's excess, and once you do, then you know it's the limiting one that you have to use to predict products. And then the calculations are going to be just like we did before. So the ones I showed you in the class last time, and the one I did as a warm-up at the beginning of class, those didn't mention limiting excess. In fact, they're worded such that if you read them carefully, they'll say, I have this reaction, and there's NO2, here's how much NO2 is in there, and there's plenty of the other reactant. That type of wording is actually in the problem, so you can ignore limiting in excess. But if it doesn't say which one in any explicit way, you have to figure it out yourself. So here's how you figure out limiting and excess, and we'll use that reaction. So here they're telling you this many moles of N2 and this many moles of H2. And here the relationship is 1 to 3. But here's how it will tell you to do this. You're pretty much always going to be limited to 2 reactants. Just kind of fundamental equations that we'll do in class over the summer. So you look at those 2 reactants and you really just pick one. For one thing you're going to need is this relationship. 1 mole, right up here out of the way. 1 mole. So the relationship of the 2 reactants, N2 and H2. So I'm going to need that. Because these are in moles, it says how many moles of NH3, and it says moles of N2 and moles of H2. When it's all in moles, you're not going to need grams per mole, so we're not going to have to calculate the molar mass of these. So it does simplify it a little bit. Okay. So we're asked to calculate how many moles of NH3. How much of this product will we get if we put this many moles and this many moles? So here's what you do. You look at those two reactants and you just pick one. Doesn't matter which one you pick. So let's just pick the first one, N2, and N2, 3 moles of N2. If we have 3 moles of N2, and I'm going to put 1 mole N2, and what do we get here? That'll cancel. 3 times 3 is 9. So we're going to end up with 9 H2. All right, if there's 3 moles of N2, as this mentions, we're going to need 9 moles of H2 to make it break even. This says we have 6 moles of H2. but we actually have 6 moles of H2. Less than we need. You see that? That means so H2 is the limiting one because we don't have enough. We only have 6 moles, but we needed 9 moles to make it break even perfect. But it says we only have 6 moles. We only have 6 moles of H2. We don't have enough. So that's the limiting one. Do you see? What if you had chosen, I said let's just do N2. I picked N2 because it was first in line. But if you had happened to choose, I have to squat here, but what if you said, no, I want to do H2 first? Well, then I would come over here. Let me remind you, this is the given amount. These are the ones that come from the equation. This is the given amount. Right. But what if instead we decided to do H2? So I'm going to flip this over, and I'm going to go over here and go, in this case, the given amount is 6 moles of H2. 6 moles of H2. And now to calculate, I'm going to use this, but I'm going to flip it over. No. 1 mole, and 2. There. Now I'll cancel. And now I'll get 6 divided by 3. I'm going to have 2 moles of N2 as a result of this calculation. Got something wrong. Oh yeah, we've got 3 moles of N2. But we actually have, let me word it the same way. We have too much N2. If there's 6 moles of H2, they're telling us 6 moles of H2 was put into this. That means we need 2 moles of N2 to make it react perfect and even. And in this case, we have too much N2. So let me back up and pretend I haven't done this calculation. When we got here and realized we didn't have enough H2 and determined that H2 was limiting, that necessarily means we didn't have to do this. We could have concluded this, and then we would say, we could have gotten both of those conclusions from just this one calculation. If H2 is limiting, well, that means N2 is excess by process of elimination. You see that? If you had chosen H2 to do this calculation, you would have found out that we have too much N2. And then we would go, N2 is excess. Because we have 3 moles of N2. We have 3 moles of N2. But if you have 6 moles of H2, then you only need 2 moles of N2. You don't need all 3. So we have too much N2, so we've decided N2 is in excess. So if we hadn't done this, we would have come here to this conclusion. But if N2 is excess, that necessarily means the other one is limiting. So down here, we conclude that N2 is excess and H2 is limiting. But that's the same conclusion. That's my point, that you can pick one, and wherever you land, the other one is the opposite. So you really didn't have to do both of those calculations. You see, I know this is confusing. You follow that? So you have two reactants. You have to figure out which one is limiting. And once you know which one is limiting, then you ignore the relationship for the other one. And you key your products based on that limiting one you figured out. So whichever reactant you picked first, we figured out that it's H2 is the limiting one. That means we're going to key on the H2 to predict how much NH3 gets produced. So now the rest of this is just like the previous calculation that I was doing, except no grams are being brought up, so we don't need grams per mole, we're just staying in moles. So now I'm ready to answer this question. Commercial process, blah, blah, blah. How many moles of NH3 is formed when you put this much N2 and this much H2 together? Well, now we can predict it. We're going to use H2 as our predictor for the product, meaning we're going to use H2 is limiting, so we're going to use H2. 3 moles of H2 to 2 moles H3. 2 moles of NH3, yes. And notice, so we went through this to figure out which one is limiting. Now I'm going to erase it because we learned that H2 is the limiting one. So I did twice as much work as I needed to, but it wouldn't hurt you to do it both ways. If it's not sinking in, I'll do more of those. Now we can answer this question. Well, let me write this down. Oh, it switched to yellow. One mole of N2 to 2 moles. Both of those relationships are there in this statement. Do you see that? There's N2 related to NH3, and there's H2 related to NH3. Well, I think I have some on. 3H2, and 1, yeah, that's right. But we figured out that H2 is limiting that one. That means this isn't going to work to predict the product, so we're not going to use it. That was the whole point of what I did here. Figure out which one is limiting, and then I'm going to ignore the one that's in excess. Use the relationship with the limiting one to the product. That's going to predict our product. So now it's just this. We're going to go H2. We have 6 moles of H2. I should be doing 6.0. All along, I should have been going 3.0 and 6.0 because that's two significant figures. 6.0 moles of H2. And now I'm going to use this, not this. And I want the H2 on the bottom, so I'm going to go and that'll predict how many moles of NH3 will be produced from this reaction when the reactants are put in these amounts. That's the whole idea about limiting in excess. The calculation is the same as the ones I was doing previously, end of class last time, right at the beginning of class today. The twist is you have to figure out which one is limiting and which one is excess, because you have to use the limiting one to predict the products. Round 6 is 12, divided by 3 is 4. Two significant figures, and these are exact. Those two, the 2 and the 3 are the coefficients up here. 2 and 3, those are exact. So that's why I have two significant figures there. You get it? Okay. So there's some at the back of the chapter. I'll make another list for today of new problems to go over. It's mostly these, though. What else is going to do? Oh, I'll do combustion too. But let's go to back of the book, 377. Put you down here. Limiting reactants, 3.7. I skipped the first few silly ones. So I'll give you an equation like this. The equation like this are implied in these few up here, so I'm just skipping those. But I want you to have it right in front of you. And this is a red problem. Y'all found the answers to the red problems in the back of the book? You just go down here, answers to red exercises, and you can find these answers. So I'll do the ones that are black, because you have the answers to the other ones. So let's jump on this one. Let's do reactant. 5 moles of this, 5 moles of that. That's all moles. How many grams? Okay. 379, 380. How many grams? Okay. So I'll do 7, 8, and 80. All right, so what do we have? So the next one I'm going to do involves grams. Notice, now that we have moles of NH3, we could figure out how many grams per mole NH3 is, and then we could convert this moles to grams. So that's the only other twist here. You could stop at moles, or you might be asked for grams, and there'd be one more step. You can also be given grams for these, so when I do 80, I think it'll show you that. So 7, 8, this is problem 3.78, right? So you have the reaction up there, you have all these relationships up here, but we have to figure out which one of these we're going to use to predict products. So it's this many moles of ALOH, 3, and this many moles of H2SO4, so that's your two reactants. And then it says how many moles of Al2SO4, this, do we get? So first we have to figure out which one is excess. How many moles of excess reactant remain? We can do that. It's really this. This is the real question. How many moles of Al2SO4, that's aluminum sulfate. Okay, so pick one, the first one or the second one. Pick one. Number one or number two? 2. So we're going to pick this one. 3 moles of H2SO4. Three moles of H2SO4. And we're going to use this relationship, these two. 3 aluminum hydroxide to 3 sulfuric acid. 2 to 3 3 moles of H2SO4. 3 moles of H2SO4 to 2 moles of aluminum hydroxide. ALOH3. You said H2SO4, 0.5 moles. It should be 0.5 moles. That goes there. I'm going to darken this in just to emphasize this is how much we actually have, and that's 3 significant figures. We have 0.5 moles of H2SO4, 0.5 moles of H2SO4. Here's my calculator. .5 times 2 0.3. So the answer is my calculator gave me 3s all the way out, but it's going to be 3 significant figures. These 2 are exact. That's how many moles I need of aluminum hydroxide to react with 0.5 moles of this. But how many actual moles of aluminum hydroxide do I have? 0.5 moles of that. I need this many moles of AlOH3 to react. I have that's all we need. So is AlOH3, is that in excess or limiting?
Excess.
You said it?
Excess.
I need this much, but I have more than that. So this is in excess. If you get confused, it's right here you get confused, but just think it through. This is how much we have. Read the question. This is how much we have. And this is how much we have of H2SO4. But this is, if we have this much H2SO4, we only need this much AlOH3. But we have more than that. So AlOH3 is excess. You follow it? If you're going to get confused, that's where you'll get confused. But there it is. You only needed this much, but this is how much we have. So we have more than we need, so it's in excess. Which necessarily means the other one, H2SO4, so H2SO4 is limiting. So we have all we need. We could go back and start with AlOH, but we're just going to come to the same conclusion. You with me here? So the limiting one is H2SO4. I'll just do this. So I won't forget in 4 seconds what we concluded. But the limiting one is H2SO4. So now we're done figuring out which is limiting and which is excess. Now I can make a calculation. How many moles of this product will form? Well, we're going to use the H2SO4 as it relates to the product, this product. That is 3 and now the relationship of H2SO4, the moles of H2SO4, in the reaction. There's 3 of those to 1 mole of aluminum sulfate. Al2SO, Al2SO. And this is just going to come out to 1. I wrote this wrong again. Three moles base, yeah, I wrote that wrong again. I should have written this, 0.5 moles of H2SO4. Right here. So now what do we get? Divided by 3, so my calculator gives me actually my calculator says this, it gives me a bunch of 6s and then it rounds that last 7. But I'm just keeping 3 significant figures. This 6 rounds this 6 up to a 7. SO4, 3. That's how many moles of Al2SO4. Okay. You with me? I used the 0.5 of H2SO4 because it was the limiting. And then I could figure out how much product I got. You follow me? So these just have a twist at the beginning. You have to figure out which one is limiting and which one is excess. Let's do 3.80. This one involves grams. Makes it a bit longer to solve. So this is going to involve grams per mole. NH3, so here's your two reactions, reactants, NH3 and O2. But they're giving them to us in grams here, and then it asks us how many grams of NO product. It's asking you both, actually. So this one's a little more involved. But let's do this first. NH3 and O2. Let's do this first. So your periodic table says 1.01 for hydrogen. What does it say for nitrogen?
14.01.
And 3.03. So that's the molar mass of NH3. So we're going to need that. What else we have? O2. So oxygen, there's 2 of them, and that's all there is. Times 16.00, that comes from the periodic table, so we'll get 32.00. And it asks us both products, so I guess we'll do all of them. So now we're on the products. There's NO, there's one of each of them. 14.01 for N, 16.00 for oxygen. .01. And what else? H2O. H, there's 2 of them. O, here's 1 times 1.01 times 16. This will be 2.02. 16 18.02 grams per mole. So since we're gonna need all of those, we figured them all in first. So it's asking about grams and it's giving you grams, so we're gonna need that. All right. So how many grams of NO, that's a product, and H2O, that's a product. So how are we gonna predict the products? We have to figure out which of the reactants is limiting and which is excess. Let's just go with the NH3. So we have 2 grams of NH3. 2.00 grams of NH3. Grams per mole for NH3 is 17.04 grams of NH3 to 1 mole of NH3. Now we're going to use the relationship of the 2 reactants, and the moles of NH3 will be on the bottom. NH3, 2 moles of O2. That's the 2 reactants, and it's 4 to 5. So now we're in moles of O2. Grams per mole for O2 is 1 mole of O2. Mole of O2 is 32.00 grams of O2. No, I lost my mind there. We were supposed to stop. No, that's fine. No, that's fine. Forgot what I was doing for a second. Okay. So we do have to actually calculate this out. That's exact. These 2 that come from the equation are exact. That one is exact. That's exact. 3 significant figures, 4 here and 4 here. So we do have to calculate this. 2 times 5 times 32 divided by 17.04. 4, I get, my calculator gives me but I'm going to keep 3 significant figures, so this will be 4.69. I need 4.69 grams of O2. I have grams of O2. How many grams of O2 do I have? 2.50 grams of O2. I have 2.50, but I need more than that. I needed 4.69. So which one is limiting? Which one is excess? I've discovered that I need this many grams of O2, but this is how many I actually have. So which of the reactants is limiting and which one is excess?
O2 is limiting.
Say again? Can't see who's talking. Hmm? You had a guess. You're not going to say it again? Like I said, if you're going to get confused, this is where I get confused. This is that one little turning point. This is how much I need, but this is how much I have. You make me say it.
O2 is limiting.
Say again?
O2 is limiting?
Yes, O2 is limiting. I don't have enough. So O2 is limiting, and the other one, NH3, if I'd started with NH3 here, or I did start with, if I'd started with O2 here, I would have found out I had more than I needed for O2. No, I would have found out I had, no, if I'd started with O2 here, I would have found out that I had too much NH3. Like I said, if you're going to get confused, this is where it'll be. This is how much I need of O2 to react with 2 grams of NH3. But actually I have only 2.5, so the O2 is limiting because I have less than I need. So again, this is where you get confused if you're getting confused, but it is straightforward. You just have to think through a couple of these problems. Anyway, O2 is limiting, so now we can move on and predict the products by using O2 as our guide. Do away with this. This was all about finding limiting versus excess. So if it's O2, now I'm going to use 5 moles of O2 to 4 moles of NO and I'm also going to use 5 moles of O2 to 6 moles of H2O. It's those that I'm going to use to predict the products. You're with me now, right? So when you practice these, think about that one critical turning point, because it is straightforward. It's just confusing at first. What am I doing? So how many grams of NO will be produced and how many grams of H2O will be produced? So I'm going to use this 2.50 grams of O2 as my starting point because it's the limiting one. And from there, grams per mole for O2 is 32.00 grams of O2 to 1 mole of O2. Now I'm going to use, I guess I'm calculating NO first. So we'll figure out that product first. So I want the moles of O2 on bottom, so I'm going to go 5 moles to 4 moles NO. But it's asking for grams of NO. This will give me moles of NO, but this wants grams, so I've got to go one more step. I need the grams per mole for NO. I want moles on bottom, so 1 mole of NO to 30.01 grams of NO. And that'll tell me how many grams. These are exact. You're getting those coefficients from the equation. This one, those are all exact. So again, I've got 2, 4 significant figures. 2.50 times 4 times 30.01 divided by 32 divided by 5. My calculator says that's a 5. 5. I'm keeping 3 significant figures. The 5 will round the 7 up to an 8, so I've really got 1.8 grams. So that's how many grams of NO that I'm going to get from this reaction. And we can figure out the water too. Figure out the water, I'm going to start the same way. I didn't have to erase that. I could have left that. Okay. 32.00 grams of O2 and 1 mole of O2. Now I'm going to use this O2 to H2O. I want moles of O2 on the bottom to 6 moles of H2O. So that's this. And then this for H2O, 1 mole of H2O. 18.02 grams H2O. So that came from here, and that's going to give us grams of H2O. It's the same deal with significant figures. We're going to end with 3. 2.50 times 6 times 18.02 divided by 32 and divided by 5. My calculator says, keeping those, the first 3, the 9 rounds the 8 out, so it's 1.69 grams of H2O. You see the process? Do practice these, because I know that one turning point confuses you. Maybe there's another one. I'm going to give you the equation like this. 3.82 kind of makes you come up with the equation. But this requires you to know how to come up with the formula from the name. Hopefully y'all are practicing that from the other chapter. But for a question like this, I'll go ahead and give you the reaction. Also this one, H6BR. No, I guess that one's balanced. Okay, let's see if I can balance this and solve it. So I'm not making y'all do balancing equations. Next chapter we'll do some. But let's see. Okay, combustion, C2H5OH. Let's see if I can do this in front of you. So for a combustion reaction, it's always some organic compound and then O2, and then we get H2O plus CO2. 2 of those. So it'll give me 4 of those. That makes 5. It's 5. I knew this was going to be hard. 6 H's, so we do this. 3 of those. 4 of those. 7, but that's not going to work. 4 oxygens, 3 hydrogens. I think that does it. 6 H's, so I get 6 H's. 3O plus 4O, 7O. Yeah, okay, that's balanced now. And that's 1. All right, I won't make y'all balance these, but so let's just answer B. Let's figure out which one is limiting. I won't make y'all solve these with diagrams either. 1, 2, 3, 4, 5, 6. So assume it gave you 6 moles of O2, 2.0 moles. It's become more and more common to use these kind of space-filling color diagrams, but you can't do that on paper, so I tend to lean away from those types of diagrams. But pretend the problem said this. You've got 2 moles of this, 6 moles of this put together. So now you have to figure out which one is limiting and which one is excess. I'll start here with this one, and I'll say I've got 2.0 moles of C2H5OH. The relationship here is 1 to 3. So 1 mole C2H5OH. 1 of these to 3 of these. 2 times 3 is 6. This one doesn't work for limiting in excess. Do you see why? I have 6.0 moles of O2. That's how many moles I needed. So there is no limiting in excess here. So that's a trick question, you bastards. Which reactant is the limiting reactant? Neither of them. I want to leave the red ones so you guys have something to practice. So I had to pick out the trick question. Great. Well, if you want to do more of those, we can. But I'll just make up a problem. What else did I want to do today? One other thing you can do with these reactions, and they have a problem like this, 3.71, but I couldn't find them doing this in the chapter, but we're going to get to a chapter where we do this. I've got to write a balanced equation for this one too. I should do 3.72. 6, 7. So I'm going to do this one, but I'm going to write the molecular formula. So there's 6, 7, 8 of those. That's it. 12, 8, and then, okay. Got that. So I won't make you do all this on the test, but okay, so pretend you're given this and pretend it's already balanced for you. Times 8 is 16, 17, and I need how am I going to do that? Nine oxygens, 16 oxygens, that's 25. This is going to look crazy. Maybe I should just make up an example. 16 carbons, 16 carbons. 102. 5 divided by 2. That's 18. 40, so this is 20. And then 36, okay, that's balanced. Good Lord, what was I trying to do? Oh, yeah. Okay, a combustion reaction, this is the new thing I was going to tell you. So, but pretend you have so J is for joules. And it's a measure of energy. You can think of it as heat, how much heat. So pretend, so I did all the balancing. Pretend you have a balanced equation and you're told that this reaction produces this many kilojoules. Like you put these two together and react, and you actually have a calorimeter or something to measure how much heat comes out. And you measure it, and that's how much heat comes out. So you have kilojoules, that many kilojoules. Without going deep into energy or any deep discussions, I wanted to show you this and put it on the test because it's so much similar to everything else we've been doing. This is easier than limiting in excess. So pretend it was balanced for you and I didn't have to do that. So you've got this reaction and it produces this much heat. In the same way previously, I told you that this equation gives you 6 relationships, this to this, 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 and this to this. 6 molar relationships. What you have now when they give you this, and they say this is how much heat came out of it, now you have 4 more relationships. Here's the 4 relationships you have. If you're given this, and you also have this, let's scale this up. Just to be accurate, let me do, I'm going to change the joules. You won't have to fix everything up like I'm doing. So I scaled this up so I didn't have to use fractions by 2. So let's say it did this. That's how many kilojoules came out of the reaction. Here's the 4 relationships you have now. 2,734 kilojoules to 2 moles of C8H18. 2 moles of this to this energy. And then you can also write down this 20 moles of O2. So there's two of the four relationships that are here. Two more relationships. Same energy, but now I'm going to say 18 moles of O2, H2O. And one more to 16 moles of CO2. That's not hard. If you're given a reaction and you're told this is the energy that comes out, now you have four more relationships that are implied by this reaction. There's the 6 molar relationships, but if you're given how much energy comes out of the reaction, now you have four more relationships, joules to moles. Do you see that? So don't feel confused just because I'm suddenly bringing up energy. We'll talk more about energy for test 2.
Is it supposed to be the same number on the
Yep.
bottom? Because you wrote 17,000 or 17,
Oh, yeah,
1,700.
thank you. Yep. Those should all be the same number on the top. These four relationships. And I've just got that written on the top for all of them. Or do I? 2, 7, 3, 4. Okay. And just like before, you're not going to use all of them in most problems. There's just one of these will be relevant. Oh God, which one was I doing? This one. Okay, I wrote the molar formula for that instead of the structural formula. Okay. And I wrote that down. I should have been using that. And it needs to be multiplied by 2. I did that. 1 mole of, okay, but I did it as 2. So 5470. So, okay, so pretend I haven't screwed up 3 times. Okay, pretend it's that. I'll just write these. Just to be complete, I'll write it all out. 10, 9, 40. Okay. That's the 4 relationships. They're saying 1 mole of this reacted, but I would have had to use a weird fraction here. So I scaled it up by 2. So that's why I multiplied it by 2. Anyway, pretend you're given this equation balanced, and you're told this is how much heat comes out. You have those 4 relationships. Okay, now write the balance equation. 1 gallon. Well, I won't ask it that way either. Well, all right, let me just make up my own question. I want to keep that one. C8, H18. Since those are the only examples of this, I might have to look. Screw it, I'll put that on test 2. This is actually easy, I'm just making it look hard because I didn't find good examples. All right, we'll do energy stuff for test 2. I'll just drop it off. I think that's all I want to do for test 1. I was going to squeeze that in, but I'll make that look way easier than I made it look today. So we're just down to you guys having questions. I told you guys I'd compile a list of test 1 questions at the end of the chapter. I just haven't yet. I'll do that before lab and give them to you then. We can hang around after lab upstairs if you have questions. So we can do that, and we have time now if you guys want to go over anything. You want to do more limiting? I have to find examples. Okay, we're not in thermochemistry. I'll give you this in case you want to look at it before lab. Limiting reactant section 3.7, and the problems I'm looking at are how I solved those. Those are the ones I'm looking at in the back of the chapter. Hopefully, I have listed good ones to do. 3.83. That's a good one. So I guess 3.84. I will do 3.84. 3.85 has the reaction for you. So 3.84 and 3.86. 3.84. So it says C2H6 reacts with Cl2. These are probably making me balance them. Main product. Those aren't going to be good examples. I probably have to come up with more examples of these for you guys. But I should have said this. Well, let me go through with this one. They just make that one sound way too complicated.
Around how many problems will be on the test?
40 to 50 problems on the test. And about half of them will be calculations, and about half of them will be other questions like naming compounds. But these, I guess 3.85 is a good one. Maybe not 3.84. All right, so not 3.84. I haven't used the word theoretical yield, but that's actually what we've been doing. But they're just making that one sound too complicated. I can do 3.86 for you. Hydrogen sulfide gas. Sodium hydroxide. But I will write out the equation for you. And I will have it balanced for you. this one is sodium sulfide and water. And 2 of those. 1 oxygen. 2 of those. No, skip 8-6 as well. I will come up with better examples for these. I have a bunch in a bunch of these somewhere. But I guess I have to find them. No, it's not that. I haven't given y'all my rant about textbooks yet. Conversions. All of them are just terrible at coming up with good questions. I keep saying one day I'm going to write my own textbook. There we go. These will be good for practice. So we'll use these. So I'll give these to you guys. The solutions are ugly, but you can see the answers. Do this one. So assume you're going to be given a reaction like that. And then this one is moles, so I'll solve this one. So I'll upload this spreadsheet. I should have relied on this spreadsheet from the beginning. Not spreadsheet, PowerPoint. Okay, so if you've got that, okay, which is the limiting reactant? We're looking at these 2 things, we're deciding which one is the limiting reactant. It's telling us we got 1.85 of NaOH moles, and we got 1 mole of CO2. So pick one, NaOH or CO2. Pick one. That's where you start with one of these types of problems. You just pick one. Which one do you want to do? CO2. CO2. All right, we have 1.00 moles of CO2. And then our molar relationship for the 2 reactants is 1 CO2 to 2 NaOH. These moles are coming from the equation. Let me write down the other moles that we have. This is saying we have 1 mole of CO2. 2 NaOH. One CO2. Na2CO3. H2O. All right. let me write this down. Here's our reactants. Here's how much reactants we have. 1.85 NaOH and 1 CO2, 1 mole of CO2. So this 2 and this 1 are theoretically the balanced equation, but these are actually what's been put together to react. So that's why I've got 1.00 mole here, and I'm going to find out how much NaOH that means. And it's just 2.00. And as soon as I write this, I'm going to say, I need that many moles of NaOH, and I'm going to say what I actually have for NaOH is this, 1.85. I actually have 1.85 moles of NaOH. I need 2 moles. So what's the conclusion?
NaOH is your limiting?
Yes.
Yeah.
You see, that's the turning point. That's the point you gotta get figured out. But as soon as you do this calculation, you'd say, I need this much. And you can go see how much you have, and you say, I have this much. And you just look right here and think for a minute. But what if you didn't say CO2? What if you said, well, let me say this. So I have 1.85, I need 2, so NaOH is limiting. That necessarily means the CO2 is excess. That was the conclusion I came to. But let's say we did NaOH first. 1.85 moles. Let's say we just picked NaOH. I'm going to use this, but I'm going to use it upside down. So 2 moles. So in theory, we need 2 moles to 1 mole. So I'm using this again, but I've got it flipped over because I got NaOH here. 1.85 divided by 2. Can you do that in your head? 0.925. 0.925 moles of CO2. Moles of CO2. I need that many moles of CO2. I have 1.00 mole. I have 1, but I only needed this much. So I have more than I need. So CO2 is in excess, which necessarily means the other one is limiting. But notice that's the same conclusion we came to up here. You just pick one and you follow it to the end. You with me? So now if I was going to predict products, so yeah, I've got it written out here. Did I finish that one out? So that's those 2 moles? Yeah, 2 moles. And then up here, NaCO, yeah. It ends up being that again. But Na2CO3 is what I have here. If I'm going to predict the Na2CO3, I have to use the limiting one to predict it. We've decided this one's limiting, so that's going to predict the product. So now I can erase all this and solve for the product. I've got 1.85. And the relationship I want is moles of NaOH to moles of Na2CO3. So it's 1 mole of this to 2 moles of that. Yeah, and it's 1.85 divided by 2 again, which is 0.925. Na2CO3. So that's how many moles of this product we'll get if we mix these two things and these amounts when they react. So we get 0.925 moles of Na2CO3. It's that one turning point, and I know it's confusing, but if you work these to that point and sit there and look at it, I have this much, I need this much in relation to each other. You can decide which one is limiting in excess. Do another one. This one limiting, these are moles. Let's do another one that's grams. So that one stays in moles. Pretty sure I have some that are in grams. So you can see where I've written all over this, but this is the reaction arrow and then products, all these products. So there's more than 6 relationships here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's actually 12 relationships there because there's 3 products. You see that there's 3 products? But we're not going to need all the relationships. This is sodium bicarbonate, this one. And this one's citric acid. I've got Ca written there. Anyway, we can solve this one. Carbon dioxide is here. So how many grams of carbon dioxide? So it's this we're trying to calculate. But we've got to start with those 2 reactants. And we've got grams here to deal with. So we're going to need the grams per mole of this, the grams per mole of this, and we're going to need the grams per mole of CO2 as well. That's what these are. So NaHCO3 is 84.007 grams per mole, and Ca, the citric acid, is 1.92.124 grams. I don't show that calculation here, but that's, I got those from one Na, so there's 3 of these and 1 of each of these, times 16 times 12.01 times 1.01. What is sodium? What's your periodic table?
22.99.
It's 3 times 16. 48. Is that right? 3 times 16, is that 48? Yeah. 10, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. I used a apparently when I calculated those, I used a periodic table that had one more digit out here. We can just go with that, 84.01. So if you calculate those, I must have calculated CO2 somewhere. Yeah, CO2 was 44.01 grams per mole. All right, so I'll use the grams per mole that's over there. All right. First reactant or second reactant, pick one. That's an easy question. You always say two, all right. So we're gonna go with the citric acid. So 1 gram of citric acid, 1.00 grams. And I'll just say Ca instead of writing it out. Grams of citric acid to moles, citric acid. And where is it? Citric acid. So we use 192.12. One mole. Now we need moles of citric acid on the bottom. And now the other reactant is sodium bicarbonate. I'll say SB. So 3 SB to 1 Ca. And now we need moles of SB, sodium bicarbonate, 1 mole sodium bicarbonate, 84.01. Theoretical yield. I don't see me doing that calculation anywhere. 1 times 3 times 84.01 divided by 192.12. My calculator says 1.3118365. 5 significant figures, 4, 3, I'm going to keep 3. So what I actually have for sodium bicarbonate and citric acid that's grams, right? Yeah. Grams of that, and then citric acid. So what am I going to write here? I need that many grams of sodium bicarbonate. I have 1.00 grams of sodium bicarbonate. So what's the conclusion? I have 1. I need more than 1, though. So sodium bicarbonate is, I have 1, but I need more than that. I don't have enough sodium bicarbonate. Sodium bicarbonate is limiting. And the citric acid is excess, necessarily. But what if we had chosen sodium bicarbonate to start with? We would have gone 1.00 grams bicarbonate. And 3 moles of sodium bicarbonate, 1 mole. So that's this. And then here. 1 mole. Okay, so that's going to give me grams of the other reactant. 192.12 divided by 84.01. 3. 762 grams of CA. I need this many grams of CA. I have this many grams of CA. I have more CA than I need. So the CA is in excess. Which means the other one, sodium bicarbonate, is limited. But that's what I found before. You see? So if you wanted to finish this out, we would use sodium bicarbonate to predict the products. This one is asking how many grams of carbon dioxide will we get. So we're going to use the sodium bicarbonate. The 3 moles of sodium bicarbonate to 3 moles of CO2 is going to be the relationship we use to predict the CO2. You see that? Let me see. So these do have the answers. So you can use these to practice. I got these out of some book last summer. Not the book we have. We'll do this stuff on dilutions for the next test. Those are the things I was trying to come up with. But this is just where we'll start for the next test. So I'll give you this PowerPoint, but you only need the limiting reactant stuff from it. A few more problems to use for practice. Any other questions? I really didn't mean to go this long today. Anyway, I meant for this to be a session where you could ask me some questions. So if you don't have any now, I'll see y'all in lab. You can stay if you want to ask some questions. We can also spend some time after lab today if you've got questions. And if you think you need further help between today and next Tuesday, email me and we'll try to figure something out to get together. You guys okay? You need to practice these? Practice them, and if you get stuck, email me, get in touch with me. I'll upload this.
Show me where these columns are.
Yeah. Let me see. Reading list. So you come right here. It's the one that literally says exercises. Click on that. And this is where they start.
I was just confused because like the numbers, with those tab.
Oh,
on that
2.9, 2.23, 2.24.
Okay.
Yeah, I should have done that in the,
That makes sense. Thank you.
you got it?
Yeah.
You guys have questions? You're just gonna work on some problems? Let me know if you got questions.
I just have some questions about the lab. So I'm sure you know that I'm Gavin Kenny.
Oh, yeah.
I was on the trip.
Um,
Just got back yesterday,
Okay.
and I know it says like print them beforehand.
You don't have to, I've been printing them.
Okay.
I'll print them for you.
And then just with the
The first two labs, the first one is technically, did you do the safety video and the safety?
Yeah.
So that's technically the first lab. The second lab, actually, I have a copy I can give you.
okay.
It's just a math lab, and you can do that at home. Oh. So that means the only lab you missed was yesterday.
Okay.
But I'll give you a copy of this, and you can take it home and do it.
And then just bring that in either later today.
Yeah, no, just you can turn it in next week.
Okay.
So it's this. And this is most of what we did last week, is this math stuff. Did you watch the videos?
Yes, I have.
I couldn't get video Thursday, and we did a lot of math stuff on Thursday.
Okay.
So if you think you need extra help,
With any of this.
yeah, let me know. But yeah, just get that done and turn it in next week.
All right. Perfect.
And the test will be Tuesday, and it's gonna be mostly, about half of it will be calculations and about half of it will be naming.
And that's just kind of the stuff from. So with last Thursday, you mainly just more math
I
stuff.
did skip some of chapter 1 and I skipped some of chapter 2.
Okay.
All you really need to do is look at the problems that I've listed on there. Did you see the Word document with
Yeah.
problems listed on? Look at those, and if you're stuck on any of those, we can talk about those. The test will be just like the problems I give you in the back.
Okay. Perfect. Thank you so much.
Oh,
Came late.
oh yeah, sign sheet. Just today. Yeah, this is the things, but I don't know why I wrote a 5-4.
What's the layout of your test?
Well, it's gonna, about half of it will be calculations, and about half of it will be questions, other types of questions like, what's the charge on this atom? What's the name of this ionic compound? That kind of stuff.
So, are the calculation ones, are they gonna be like multiple choice or like short response?
I probably won't make it multiple choice just because you have to do all the calculation anyway. If I did make it multiple choice, it would be to make it easier for me to grade.
Okay.
But you'd still have to go through the whole calculation and
Right.
give your answer.
Okay.
Between 40 and 50 questions probably.
And we have like. a
You
whole
should have
class
plenty
of-
of time. Yeah, I'll give you the whole class period. I'd even give you more than that if you needed it. I don't like to make the test time-based.
Right. Okay.
But you just need to make sure you're comfortable with these calculations. The questions that are assigned at the back of the chapter. If you're comfortable with all those questions, then you're ready for the test, because I'll ask questions just like those.
Okay. Okay, thank you.
I know. It's got like no hair to it.
Stuff.
Yeah, I really didn't know where to park, I didn't realize